Hello, pre-calc students. This is going to be logs day 3. So today we're going to be talking about how do we graph a logarithmic function, and then more importantly, how do we determine the domain of something that is logarithmic in nature. So to get started, we're going to consider a function that I'm hoping we're pretty familiar with at this point. We're going to look at y equals 2 to the x. And within y equals 2 to the x, you can see that I already have a lot set up here. So if you want to get yourself set up with some notes here, we're going to have a table of values off to the side just to kind of quickly remind ourselves what 2 to the x looks like and be a little bit more accurate than just sketching the general shape of the graph. Then you'll see over here, I'm going to list some properties of y equals 2 to the x. And then we're going to compare it to its inverse equation. And hopefully in your mind, you can think about what the inverse equation is. And we'll talk about how we're going to form the inverse. So to get started, let's go ahead and fill in the rest of the chart here. If we have 2 to the negative second power, that's 1 over 2 squared, which is 1/4. This would become 1/2. 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4. So hopefully we can generate that table of values pretty quickly, such that if I plot those points, negative 2 1/4, and negative 1 1/2, 0 1, 1 2, 2 4 would be up here. Okay, there's a nice sketch of y equals 2 to the x. So I'm going to come over here now, fill in the key information associated with this graph, and then we'll talk about, well, what does the inverse graph look like? So the y-intercept is right here at the point 0, 1. The x-intercept of this graph, we know it actually has none because there's that horizontal asymptote that we're approaching. So that's the next thing we're going to fill in. Y equals 0 is the horizontal asymptote for this parent function. The domain of an exponential function, really any exponential function, but specifically the one we're looking at, would be all real numbers. So you can plug in whatever you want for x. You can do 2 to whatever power you'd like. But as far as the range goes, because of where the horizontal asymptote is, we can see that it's only from 0 to infinity, where 0 is not included. So these are all things that I'm hoping you're, like I said, very familiar with, comfortable with being able to determine based on what we know about exponential functions and their graphs. So let's move on and talk about the inverse of this function, y equals 2 to the x, which would be y equals log base 2 of x. Okay, so if you were to rearrange this, switching x and y and getting y alone again, you should get y equals log base 2 of x. I'm going to list the same information, y-intercept, x-intercept. I'm going to cheat a little bit because I know it doesn't have a horizontal asymptote, but I'm going to put this instead. You'll see why in a moment. But we can still list the domain and range as we normally would. All right, so before I go and fill in all this information, let's see what the graph looks like. And how am I going to form the graph based on 2 to the x? Well, we know when we find an inverse, we switch x and y. Well, good thing I have a nice little table of values to be able to switch the x and y values with. So instead of having negative 2 1/4, you would have 1/4 negative 2 down here. And then you would have 1/2 comma negative 1. 0 1 becomes 1 0. And then we're going to have 2 1. And then finally 4 2 would be over here. So the graph for log base 2 of x, you can see, is going to look something like that. And if you're looking at those two graphs and you're like, oh yeah, I kind of remember that relationship graphically between a function and its inverse. Well, when you switch the x and y values, maybe you remember it's a reflection over the line y equals x. And that's exactly what the graph implies here, once I switch the x's and y's. So now when I come back over to my list over here, the y-intercept for log base 2 of x is non-existent. It will not cross the y-axis. No matter how close I get, we know we're approaching a, not horizontal, but vertical asymptote. So now it has a vertical asymptote at x equals 0. And as far as an x-intercept is concerned, the x-intercept is at 1 0. So the parent function for log base, really anything of x, will be at 1 0. Domain we have to be a little bit careful about. It's no longer all reals. It starts at 0 and then heads to infinity, which makes sense to me because remember, the range of a function becomes the domain of its inverse. And therefore, the domain of a function is the range of the inverse. And this makes sense. It looks like it's going down forever. It's going up forever. So the domain and range do get switched when we're talking about a logarithmic function as compared to an exponential. So knowing all this information, I would say, is pretty important in being able to sketch log functions. And then what we're going to get into, like I said, more specifically today, is talking about the domain of log functions. Okay. So let's kind of talk about this domain concept. Apparently, when I take the log of something, it has to be a positive amount, which makes sense, because if it was log of a negative, we'd be saying that something to a power equals a negative number. Will something to a power ever equal a negative output? No. We know that based on the graph of an exponential function. So let's talk about, in general, domains of logs. So in general, the domain of log base b of a quantity. And I know that probably looks a little bit weird that I'm just putting some random rectangle in there, but it doesn't matter what's inside the rectangle. If you're taking log, doesn't matter the base either, of some quantity, what you're going to do is take that quantity on the inside and set it to be strictly greater than 0. I promise we'll practice with this in just a moment, but whatever you're taking the log of, separate it from the log and say, you know what, I have to be making sure that this quantity is greater than 0. It can't be equal to 0, by the way, right? We've got a vertical asymptote that we're contending with there. So you can't take the log of something negative. You also can't take the log of 0. Because of this horizontal asymptote in the exponential, will anything to a power ever give me a 0 as a result? And the answer is no, it will not. So this greater than symbol is pretty important. We can't just, throw an equal to and assume that we're going to have the same results here. So let's do a little bit of practice. If we have y equals, we'll start kind of easy. Y equals log base 2 of x plus 3. Well, we just graphed log base 2 of x up here, and what we'll do by the end of the lesson is talk about what kind of transformation is occurring to the graph if we put an x plus 3 on the inside, which you probably already know. But if I'm just asking you about domain, you're going to say, well, x plus 3 has to be greater than 0. So take that quantity out, right, whatever's in the rectangle, and say that has to be greater than 0. It has to be positive, so therefore x has to be bigger than negative 3. The domain would go from, in interval notation, negative 3 to infinity. And that's it. So if you remember the rule, that's good. I mean, I also want you to understand the concept graphically as to what's going on here as well. Let's take a look at y equals ln of 2 minus 5x. Okay. Now, I don't want you to be scared off by ln, because I said log base b. Does this fit the form log base b? And the answer is yes, it does, because ln is the same thing as log base e of x. Okay, so log base e, ln mean the same thing. So therefore, if we said, let's let 2 minus 5x be greater than 0, whole quantity on the inside, when I solve, I'll subtract 2 to the other side, but I just have to be careful that when I divide the negative 5 over, this inequality flips over. Okay, so we get x is less than 2/5 when I do this. So to be less than 2/5, the domain would be from negative infinity to 2/5, and we'll never include that endpoint, because that would be making this 0 on the inside. You can't take the ln or the log of 0 for that matter. All right, let's try a couple more. Let's do log base 4 of x squared minus 3x minus 10. Okay, so to find the domain here, we want to make sure that x squared minus 3x minus 10 is greater than 0. Now, the second we get a quadratic on the inside, I want you to be jumping in your head to thinking about, how do we solve quadratic inequalities or polynomial inequalities? You must partition, okay? So we're going to have to figure out what are the roots and then partition around those roots. This is a process we've done many times before. And look at that, it's back. So find the roots by factoring x minus 5 and x plus 2 equals 0. Well, again, if it's greater than 0, you're going to treat it as if it's equal to 0 real quick to get x equals 5 and x equals negative 2. And go ahead and put those on the number line. Negative 2 goes here, 5 goes here. I'm going to do the partitioning real fast because it's something we should be familiar with. But one thing we can note is that these have to be open circles. Can't include them if we want to look for greater than 0. So if I plug in -3, -3 minus 5 is negative. -3 plus 2 is negative. So altogether, that's positive. And this is going to be a really familiar looking process. Plug in 0, 0 minus 5 is negative. 0 plus 2 is positive. So altogether, that region's negative. And if you plug in 6, you will get plus plus. So we're looking for positives. We're looking for greater than 0. We're going to shade in these outer regions right here. So therefore, the domain of log base 4 of x squared minus 3x minus 10 is from -infinity to -2. And then from 5 to infinity. Okay, so even though that would be a pretty tough one to sketch based on, let's say, function transformations, we could still find the domain of that pretty easily just by solving a quadratic inequality. So we have to know at that, what that process looks like in terms of partitioning. But once we get to that stage, the process really isn't something we're not familiar with at this point. Okay. So I think that's good for domain for now. Next time we're in class, we'll definitely get a little bit more practice with this concept. But just looking at those 3 examples and reminding you that, oh yeah, if it's quadratic, you got a partition. I think we're probably good to go as far as that is concerned for now. Let's recall from the last page what the graph of log base 2 of x looks like. So we're going to do some function transformations here. So if we have y equals log base 2 of x, some of the key things that I'd want you to sketch when you make your graph of log base 2 of x is similar to that of exponential functions. For an exponential, we probably would plot the y-intercept to make sure we approach the horizontal asymptote correctly. For a log function, I'm going to expect the x-intercept in the right location, sketch the general shape, and then make sure that you're approaching the vertical asymptote at x equals 0. So that's kind of the general form. I want you to think of this for today as being the parent function. But what I'll tell you is really that anything of the form. So anything of the form y equals log base b of x, where b is greater than 1, looks like this. So it is important to note that the base has to be bigger than 1. If the base was something like 1/2, maybe we'll look at that at the end of today's lesson. But this would be the same ideas as far as the graph goes. If it was log base 3 of x, log base 4 of x, they would all have the same general shape. So that's kind of a good point to make and a good thing to take note of. If I said, hey, sketch log base 3 of x and some transformations, they're all going to start off with this general shape, and then you would kind of go from there. So I kind of alluded to this on the front that we actually found the domain already for log base 2 of x plus 3. So let's sketch the following. So if I have log base 2 of x plus 3, what does that do to the graph? Well, based on what we know about something that occurs on the inside of the function transformationally, this is going to shift the entire graph to the left 3. So if I compare this to this graph up above, shifting everything to the left 3, we're now going to, if we had an x-int before at 1, it's now going to move over 1, 2, 3 to -2, 0. There's my new x-int. The vertical asymptote, when I shift horizontally, will move with it. So we get x equals -3 as the new VA. And if I sketch the general shape, you'll notice that we will cross the y-axis. I'm not too concerned about you crossing in the exact location there. We can find that exact location if we wanted to. But just knowing that the graph does shift to the left 3 units, carrying that x-intercept over, I think would be a nice thing to do. Okay. So if I move this such that we graph in number 2, y equals log base 2 of x minus 2 plus 1. So I'll add another transformation on there. So just the log base 2 of x minus 2 part to begin with, that's going to shift to the right 2 units. And we know that changes on the outside is going to be the vertical shift up and down. So that's going to move up 1. So if I think about going back to the parent function, we want to move this point to the right 2 and up 1. So that looks like it's going to be at 3, 1 now. And because we shifted everything to the right 2, don't forget to move the vertical asymptote with it. So the vertical asymptote is at x equals 2. And then sketch that general shape. Here we go. So as compared to the original, it should look like we took everything, moved it to the right 2 units, and then up 1 unit. All right, let's do a cut, maybe just a few more. So if I said 3 log base 2, putting a 3 out front of number 3. Okay, let's sketch 3 log base 2 of negative x. And maybe for this one, to get the idea of what's happening here, we'll do it in a few stages. So what I mean by that is I might start this one by sketching the general shape of just, this is the parent function. There's log base 2 of x. So when I negate the x on the inside, negating x, I'm hoping what you're thinking will happen is we flip it over y. So we're going to reflect over the y-axis. And then after that, the 3 out front, that's a vertical dilation. So it's a vertical stretch by that scale factor of 3. So, and it should go in that order. So let's go ahead and flip it over the y-axis first. So if I do that, now we have an x-intercept at -1. So the general shape's going to look like this. It doesn't change where the vertical asymptote is, right? That's only going to change if you have a horizontal shift somewhere. And then tripling those y values, if you think about what that's going to do, is it's going to make the y values, in this case, more negative. And then over here, it's going to stretch them out and make them more positive. So if you think about whatever these y values are right here, for example, a y value of -1 now becomes a y value of -3. And once I cross through the x-axis, tripling the y values on this side, it's going to stretch the graph out vertically. So your final answer, when you multiply everything y related by 3, is it's going to stretch out this way, and it's going to stretch out this way as well. So I think having this to compare to and say, hey, what happens when I put that 3 out front? You can see we definitely took the graph and we stretched it vertically by that scale factor. Now, I didn't even really choose any specific points here. I just kind of tried to make the curve appear that it was vertically stretched. If you wanted to pick a few points and multiply the y's by 3, of course, you'd be well within your rights to do that. Last thing I'm going to do transformationally is sketch y equals, let's do negative log base 2 of x minus 1. Okay. So if we want to graph the negative log base 2 of x minus 1, we know we're going to shift to the right 1 unit. So instead of having an x-intercept at 1, now we're going to have an x-intercept at 2. The vertical asymptote would shift 1 unit to the right as well. So there we are at x equals 1. But finally, negating the base, what is that going to do? Or negating the outside, I should say, of the log. When I negate the outside of the logarithm, what's going to happen is it's going to flip over the x-axis. So flip over x. So come up here, look at the parent function, think about flipping it over the x. Now it's going to increase towards the vertical instead of decreasing towards the vertical. All right, and then on the other side, it's going to kind of slowly head off to negative infinity. So when I sketch this graph, it's going to increase towards the vertical asymptote like this. And when I come over here, it's gonna slowly head towards negative infinity, flipping over the x-axis. But think about how that would look if we flip it over the x. All right. Last but not least, the last thing I want to talk about in this lesson is I said that this was only the form for a base of the log that's bigger than 1. But certainly we can graph these log functions if the base is between 0 and 1. So for example, if I said sketch log base 1/2 of x, what you're about to see is the form for any log base such that the base is between 0 and 1. So this will fit the general shape if the base of the log is somewhere from 0 to 1. So what I'm going to do to help myself out here in terms of thinking about what the sketch looks like is I'm going to sketch 1/2 to the x. So let's compare it to its inverse, which is y equals 1/2 to the x power. So that would be an exponential function that is decreasing or decaying as time goes on. So here's 1/2 to the x power. So if I think about taking some of those points that I just plotted and flipping them over the line y equals x right here, what does that graph look like? I'm going to graph this in red right now. So I plotted the point -1, +2. That's going to become the point 2, and then -1. Okay, 0, 1 will become 1, 0. If I think about the point 1, 1/2, that's the point 1/2, 1. And what you'll see is that the closer I get over here, when I take those points and switch their coordinates, that's going to make us approach the vertical asymptote at x equals 0 faster now. So we're going to see a graph that actually looks pretty similar to this one right here, our flipped over log base 2 of x function. You're going to see this graph right here. So this is log base 1/2 of x specifically. But if I were to transform and I say, hey, it's log base 1/3 of x, it starts off with this same general shape, and then we can move it left, right, up, down, flip it over, and all those good things, okay? All right, so that's a little bit of a log domain today, some log sketching, much more practice to come next time we're in class together. Have a great rest of your day.